Hey, honest Calc. So I just made a 17-minute video, but then threw it out 'cause anyhow. But taking another shot here because I'm getting more clarity the more I'm working through these. But if you didn't watch the video I posted earlier on Thursday, I found my mistake. It was because I was incorrectly putting -8 to the -1/3 power. I was just putting it to the 1/3 power, so it should have been -1/2 instead of -2, which then made this positive as Nia had identified. This simplifies to 4 plus negative, or if you could think of it as 4 minus 7/3. So it's 12/3 minus 7/3, which indeed give us a positive, which is 5/3. But anyhow, it's increasing, decreasing, then increasing, just like we saw on the graph. So if I go to my interval notation, which I already have written here, it's increasing from -infinity to -6. Then we've got this gap, and then it's increasing again from 0 to positive infinity, and it's decreasing in between -6 and 0, using all parentheses because we're not including those specific values. So now I have a maximum. Well, think about it this way. If it's increasing to decreasing, just draw a little sketch. Yes, that's a maximum at -6, but let's actually find out what the output is. So I could just plug in -6 into my function. Oops, f of -6 equals -6 to the 2/3, and then it was -6 plus 15. I'm just going to go right on my calculator, because now we're trying to find a specific value, not just positive or negative. And then that'll be times 9. And it's we have an output, a maximum there of 29.717 if I round to the thousandths. And then it goes at 0 from decreasing to increasing. It's actually a cusp like this. But any way you go, decreasing to increasing, it's a minimum, right? However you want to draw it, whether it's a cusp or a smooth curve. So at 0, and when we plug in 0, right, f of 0, into my original function, 0 to the 2/3 times a quantity, well, it's just going to be 0, and it indeed has a minimum at the origin. So this is another place I feel like I realized we could have taken this a bit further. It's going to make it much nicer to find the second derivative. So I'm going to do this, and then I'll tell you a moment where you can pause if you want to take those next steps on your own. So I'm going to copy this, drop it down here. Okay, so this should have been simplified a bit more. I would say, because check this out, watch what's going to happen here. If I go ahead and just divide both of these, I would get, this would become 2x to the 2/3 over 3 plus 10 over x to the 1/3, and I have x to the 2/3 plus this. And so actually that was a simple step for simplification, because now 2x, this is like a 1x to the 2/3, so I could make it 3 over 3 to get common denominator. So this is just common denominator is 5 to the 2/3 over 3 plus 10 over x to the 1/3. This is going to make it much better to find your second derivative when you go to find the concavity. So if you'd like to pause it here, please do. And take a gander at it yourself. But I'm going to keep working through it if you'd like to keep watching. And I think this is more of like the standard form that I should have told to you earlier today as well. Well, so if you want to pause and now take a gander at these next two steps, which were the, finding the concavity intervals and the inflection points. So I'm going to go ahead now and go to try to get my second derivative. So pause here if you want to do it on your own. So the second derivative, now I could just power rule it. So I could pull the 5/3 over times 2/3, and then this will be times x to the negative 1/3. Oh my goodness, so much nicer. And then maybe I'll take the derivative of the second part as 10 to the negative 1/3, so that'll be plus a 10 times the negative 1/3 times an x to the negative 4/3. OMG, so much nicer. Let me say it again. So it's 10 over 9 x to the 1/3 plus, no, it'll be minus, because I got a negative 1/3 there, minus a 10 over 3 x to the 4/3. So that was actually pretty nice for finding my second derivative. Actually, nicer than finding the first. This is a 4/3 there. Let me make that clear. So now we sort of find the critical point of this one, where it could possibly have inflection points. So we're trying to find those possibilities to use our sign chart on. Where could x, well, x can't be 0 again because we've got this, so we could try out 0. And I'm not sure what the other one will be. And let's set it equal to 0 and see what gives us out 0. So we get 10 over x to the 1/3 minus 10 over 3x to the 4/3. So now we got a lot of flexibility. I could even multiply everything by x to the 4/3 to get these out of the denominator if I wanted. Or maybe even by 9x to the 4/3. That'll cancel this out and that out and leave me with just 10x there. Minus, cancel this out, and leave me with 3 times that, 30. Oh my gosh, look how nice that is. 30 equals 10x, x equals 3. Some heavy duty algebra. So we'll test 0 and 3. So my second derivative at 0, does not exist. Here it's 0. We'll see if either of these are inflection points. So let's test out in my second derivative a few values. Maybe we could do -1, because it's a perfect cube and it's less than 0. So f double prime of -1 would be 10 over -9, that's nice, minus 10 over, this will become positive because it's a 4/3 cube root to the 4th, so it's over, so this is a negative minus a negative, so it'll be negative here when we test it out, -1. So it's concave down. Let's try in between. Let's try f double prime of +1. Okay, that'll give me 10 over +9 minus 10 over 3. Ooh, so 10 over 9 is a smaller number. This is 1 1/9, and this is 3 1/3. So this would be negative still. So this is not an inflection point here. Let's try a value to the right of 3. Because we've got all these 1/3 powers, I'm going to choose 8, which is my next perfect cube. So that'll give me 10 over 9 times 2, or 10/18, minus 10 over 3 times 2 to the 4th, which will be 16. 2 times, like 4 times 4, 2 times 2 times 2 times 2. So look, you can see 10/18 minus 10 smaller pieces. What is that going to give me? 32/48. So this is going to be positive. Yay, I found an inflection point. Yay, this has some positive concavity. So intervals of concavity. It is concave down from negative infinity all the way through. We're just going to say it's all the way through to 3. And then it's concave up from 3 to positive infinity. I mean, this is like, I guess, where I have seen it done different ways. Like, this, you might say, well, it doesn't have no concavity there. But if it's infinitely small, then it has no space where it actually is that concavity if it's only at an instant. I don't know. That's going to get us into a whole philosophical discussion. And then D becomes quite straightforward. We have an inflection point now when it changes concavity. So it's at 3, and let's find the output. So all the way back to my original function. I think I got it memorized by now. 3 to the 2/3 times 3 plus 15, right? That would be my original function when I put 3 in. Let me go to my calculator for this one. 3 to the 2/3 times 3 plus 15. Bam! 37.4415 or 442. Ooh, so let's look at our graph. Let's throw that Jansky on there. 30, wow, that's a beautiful thing. Let me slide this over. We did it. We accomplished all of our goals, so you can feel happy about this. Maybe even pause and did it on your own. Took me a few tries myself. That's why it's my second chance making a video. But so f double prime of 3, you can see right there is actually where it changes concavity. It's kind of hard to see. We can see it's concave down, and then because it got this cusp, it's actually still concave down, but then it becomes concave up. And if we look up here, you can sort of see it starts twisting up more. Well, yeah, you can see it. And look, we confirmed that Desmos is quite smart. You can put the function, do f double prime of 3. So like if you wanted to do the sign chart with Desmos, that's the nice thing. You could do f double prime of 1 like we tested out. Oh, it's negative. Try -1. Oh, it's negative also. So that's why we knew 0. But then we tried something to the right, 8. Yes, it was positive. Slightly concave up, which is maybe why it's not so obvious to the naked eye. But we tackled our goals, and now I can go to bed feeling like I am accomplished and I persevered through this problem. I'll post another one in case somebody wants to tackle one in addition. A website for finding derivatives or second derivatives to check them as you're working through any of these I mentioned in class. There's one, mathway.com/calculus. I think it won't give you a breakdown of the steps, but it'll at least check your answer. Sometimes it may look like different format, kind of like we didn't necessarily get to this format in class, but we saw that getting to this format really helped with finding the second derivative much more easily. If you stuck with me this long and watched the whole video, thank you. We did A, B, found the inflection, max, mins, and we did C, D over here, concavity, and the inflection points. I'll post another one in case somebody would like to tackle an extra one, but I hope you get some rest and have a nice day, and yeah, thanks for watching, those of you who are with me right now. Peace and love.